So back to statistics. It's a good time for a nap after lunch. So yeah, no, I'll try to keep us awake. Let's see if we manage. First of all, let me draw a few conclusions from what we saw until now, and then probably we can take on a couple of exercises with code, but that will be when we get to the right point. So I think I made the point often and deep enough that even the simplest of the problems can be mishandled if we don't pay attention. So pay attention to the PDFs, pay attention to finding correct estimators, pay attention to correlations, for instance. Huh? Yeah, correlations may produce surprising results. And surprising means that it is counterintuitive sometimes, that you need to think hard. And then the math will help you sorting this out. But as I was mentioning earlier, that there are problems that are not solved, that it is still debatable how to combine results. So this is remarkable, I think, that in 21st century we still are discussing. And part of the reason why we are discussing is that even statisticians don't agree on the procedures, because there are frequentists and Bayesians, and they have different questions that they want to ask for the data. Even if we marry the frequentist standpoint, we have to decide sometimes on the procedures and what we want. If we want perfect coverage, for instance, or if we want shortest intervals, we can have both sometimes, not always. And so there's a number of foundational issues, and we have just scratched the surface here. Yes, the PDF. Please remember to think deep about what is the distributions that your data are coming from. Okay. Now, practice lesson. Well, we will see some practice, not a lot, but we will have to go through some stuff. We already mentioned that frequentists extract p-values by asking a very peculiar question. What is the probability that I get a result that is at least as strange or extreme or odd or improbable as the one that I actually got? So this implies that we are taking a tail probability integral. That is that you have a distribution of possible results of your measurement, and this is under the hypothesis that you are contemplating. For instance, if the standard model is true, is it possible that I make a search for a certain kind of events, and I expect to find 100 events from background sources, but then I see 130 events. So I will ask myself the question, yes, I found a result that is out here in the tail. So what is the probability that I should see this result? The probability to observe exactly 130 events is meaningless. It doesn't say anything. It's just a random value, right? What is interesting is the integral from this point to infinity. This is what is called the p-value, okay? And that is what frequentists want. So in this case, let's look at the p-value of Poisson data. And without nuisances, this is an easy problem. But when we start putting in a systematic uncertainty, we start having trouble, as we'll see. Then we'll look at how we can decide what model to pass through our data points. And then also we go to understanding confidence intervals a little bit better today. So there's a number of macros that you can access in the website that's here. And you can download them if you want. You don't need to download them all, but we will go through some of them. We will not be able to look at all of them. We will use the macro die3 A.C, I think, A.C, yes, to check the coverage of likelihood intervals later on. So Poisson data. We want to write, but it's already written, it's there, but we will just look at it and maybe run it for a few examples. A root macro that inputs expected background counts. In a counting experiment, you expect a certain background from the null hypothesis with no uncertainty. So you assume that you know the background precisely, okay? Infinite precision. And you have an observation, a certain number of events, n, and we assume that you are looking for a process on top of the background. So there is no interference between background and signal, so you observe an excess of events if you have a signal, and you don't expect to see an excess of events if there is no signal. So the background should be the mean of the Poisson in that case. And so we want to extract the p-value and the z-value. The z-value is the corresponding number of standard deviations for a unit Gaussian that has the same p-value as the one you got in your case. So what you do is you take the Gaussian as a reference. This is whatever it is. It's maybe a Poisson distribution if it's discrete, or it may be whatever. Okay, it doesn't have to be smooth. It is a PDF of your estimator. And so G of theta, we called it sometimes, no? Or better, G of theta hat given the true value theta, distribution of the estimator. And we extract the p-value, and then we translate it into the number of sigma, so 1, 2, 2.5 sigma, that corresponds to the p-value that we have found in this distribution. In this case, it will be, I don't know, 5, 10 to the minus 3 or something like that. So what I'm saying is that you can convert the p-value in a z-value that tells you the number of sigmas that you are away from the center of the Gaussian distribution. The equality is this between the two tail probabilities. But this is a unit Gaussian, this is whatever it is. So even if this is not even known analytically, you can still get a p-value by sampling, for instance. All right, so for the Poisson, the case is easy. We have the distribution. And to get a tail probability, a high-end tail probability, of course, you don't have to sum all the numbers from n to infinity. You sum the number from 0 to n minus 1, and you take 1 minus that number. That will be your tail probability. And that is easy to do with a computer program. And this is the example that we have, and the computer program will draw the Poisson distribution for the specified B number, and it will highlight the region which has at least n event counts. And then it will spew out the p-value and the z-value with two simple formulas. And the p-value that you can convert to a z-value, this is the formula for a one-tailed test. So when you're looking in one interesting direction, because you can also think about a two-tailed test when you share the probability distribution between the high-end tail of the Gaussian and the low-end tail. And in that case, you are asking the question, how often am I as far away from the mean as this p-value? But mostly we do one-tailed integrals, okay? So, yeah, so I want to just run it for a few cases, just that so that we can get a feeling of it. So let's do that. I will need to get out of here. And the distribution is somewhere. I can, all right, we can leave this running. I'm running a minimization problem that takes forever, but okay. So I can do .l, Poisson. Oh, you cannot see my screen. Duplicate. Poisson, prob x, .c plus. So I'm compiling the macro. then I can call it. So let me ask you, let's imagine that, let's see what your feeling is. Imagine that you have a background of 10 events, and you observe 18 events. What is the probability that you observe 18 events if your background average is 10? Shoot a number. Somebody say a number. 18 versus 10. 1%, 1 per mil, 10%. Nobody wants to play this game with me. I'll play it. For me, 18 given 10 is a probability of, say, 2%, 1.5%. I got close, 1.4. You see, I have a sort of feeling for this. This corresponds to 2.2 sigmas. What was my reasoning? 18 is 8 plus 10, okay? It's 8 more than 10. 10 has a uncertainty, a variance of 10 is 10 because it's a Poisson. The square root of 10 is 3.1. I am at 18, so it's more than 2 sigma away. But we are in low count regimes, so the probabilities get enhanced a little bit. So it's a little bit more than 2 sigma. 2 sigma is 97%, so 2% should be the answer. Can we try again? What is the probability that I see 10 events if I expect 3? Anybody wants to try? We can talk about probabilities or z values. That is even easier, right? How many sigmas? Who says 2 sigmas? 4 sigma. Who offers more? Who says 4.5? Nobody? Okay. Okay. The probability in this case is, okay, it's 1.1 per mil, which is 3.06 sigma. Okay, less than 4 sigma. Let's try again. I think it's fun, but you might have a different idea what fun is, of course. But okay. What is the probability that we see 9 events if we expect 1? So 1, the variance of 1 is 1, the square root of 1 is 1, so we are 9 standard deviations away. But you know, we are in small statistics regime, so 6 sigma. Does somebody say something less, something more? Let's try. It's actually 4.72 sigma, not even 5. So with small numbers, this uncertainty of 1 of the Poisson seems like it's 9 sigma to go to 10. But actually the p-value is larger because it's a discrete distribution, the Poisson, and so it cannot fill the gaps all in between, so to speak. Anyways, okay, this is the macro, okay? And this is the simplest macro that you can write that does this integral. I need to go back to my slides. Yeah. One intermezzo. I used the Earth inverse function to get a z value from a p value. The Earth function is the integral of a Gaussian, and it's defined as this, and you see it plotted here. And it's often encountered in this kind of problems. When you have a Gaussian, you can often have to integrate it, and it's not analytic, but you get the expression. You have code that computes it in the macros that I provided. And this is the integral of the Gaussian. And the Earth inverse function is the one that we use to convert the p-value to a z-value, and it is this function. The implementation of the code that you just saw is just these few lines of code. And you see that we are doing a sum of from 0 to n minus 1, and we are integrating the Poisson, and then we do 1 minus sum, and then we convert to a z number by doing this formula. Sorry, why is it? Okay, sorry, this slide is screwed up a little bit. So now we want to assume that the background is not fixed, but it has an uncertainty. This is most often the case. You have typically a Gaussian uncertainty on the background, but most often you will have a Poisson uncertainty on the background because you estimate the background with a sideband. So you count events off of your signal region, and this is also event counts that come in as a Poisson process. So it will have an uncertainty that is Poisson, which means the distribution is Poisson. So if I observe 10 events in the background, in the sideband region, and the sideband has the same extension as your signal region, then the background in the signal region is also expected to be 10 plus or minus square root of 10. So it's a Poisson uncertainty, okay? But often instead you have a Gaussian uncertainty on the background because you are in large statistics regime, you run a Monte Carlo or something like that. But the background will change matters. What we have to do in our macro is to throw a random number for the background that is sampled from the PDF, in this case Gaussian. I implemented the Gaussian in the code that you have because it's simplest. You run a random number with a mean of B prime with a sigma that you have specified, how much of the uncertainty you have on the background, and do this a large number of times, always computing the p-value, and then you report the average p-value. Or you could report the median p-value. Actually, the median would be more precise if you ask me, but other people might have a different opinion. When you test this procedure, you might discover that you need to enforce that the background be non-negative. Of course, because it's event counts, it cannot fluctuate below 0. The background cannot be negative, okay? But if you let a background float with a Gaussian distribution, it will eventually get you a negative result. So what do? You have assumed that the background behaves as a Gaussian, but in fact it isn't, because the Gaussian is infinite tails towards minus infinity. So you have to truncate it, or you could truncate it or take the negative part of the Gaussian distribution and integrate it and then add it to the first bin and do something like this. So depending how you treat these cases, you are modifying the p-value, the PDF of the background, and this will modify your calculation of the p-value. So there are subtleties in this mechanism. Have you truncated? Have you winsorized? What have you done with the tail of your PDF? Anyways, we can easily implement this in the software that you have, and we can play with it. Let's not do it because it takes a lot of time to fiddle with the root macro. But okay, anyways, we have to be careful with this. And if you play with it, you will discover that adding some uncertainty, even a small uncertainty on the background prediction, will blow up your p-values. So it will be not so strange to get a result that is far away from your expectation if the mean of the Poisson is can be variable, and you don't know how much it varies more. Well, you know that it varies with a certain uncertainty. So I think that playing with this a little bit gives you some feeling that is good to have. This is a possible implementation where, well, there is a double loop, and inside the big loop, you fluctuate the background, but let's not go into that. The assignment for you for tonight, if you have the guts to do it. By the way, I know that at least one of you did the likelihood for the cosmic shower in the end. So it was not totally wasted time for me. You can change the code that you have to implement a log normal model of the background and precision. Because actually the log normal is a much better model for the uncertainty for the PDF that you're sampling your background from. Maybe it could be Poisson, but the log normal is good because it's answering the question of by what factor is the background wrong? It's not us asking the question by how much the background is wrong. Because, okay, the background is 10, but it could be 13 or 7, so I'm shifting it, I'm giving an offset, okay? It's like a Gaussian. Instead, if I have a factor, I say, I know the background to be 10 with a 10% precision, okay? This is more likely to be the case, that you know the background with a certain fraction. And that is a multiplicative factor, and so it is modeled with a log normal distribution. So I know the background to within a factor of 2. What are you going to use? A log normal. I know the background to be that plus or minus something. What are you going to use? A Gaussian. Okay? This is also what you have when you have a luminosity uncertainty in your data, for instance. You will model the uncertainty as a log normal. The log normal is the limit factor of a product of small factors. Well, like the Gaussian is the limiting distribution of a sum of many small factors. To model a log normal, if you don't have it in your random number generation, you throw a Gaussian number and then exponentiate it. But you need to also think at what is the background, how you want to specify the background. You will find out that you will need to divide the sigma that you want to quote by the background that you have to be able to run it. Here are a few examples of log normals with various mu and sigma. This is the expression, this is the variance, and the expectation value of the log normal. It's 2 lines of code really to do it, but you should try it and see what happens and maybe report some funny results when you have. Okay, you could ask, we could make the problem as follows. Implement that and then tell me by trial and error what is a 5 sigma result for an excess of events over a background of 10 plus or minus 10%. So this is a log normal uncertainty of 10%, and you have, so 10 plus or minus 1. And what is the point at which you can claim a signal at 5 sigma? Is it 20? Is it 18? Is it 25? Up to you, okay? Or you could ask the other question. What is the 3 sigma effect for a background which is modeled by a log normal of mean 3 with an uncertainty of 20%? Okay, you can try answering these questions with the code. Good. Now, let's move to finding the right model to fit your data. That is a very important question. It's very important for us because we don't know what our model is that we are drawing our data from. That is, we know the PDFs of the proton and the protons that we collide, the PDFs of the partons inside the proton. We know how to model these collisions. We know the standard model and all the interactions, but in the end, we cannot access the probability density functions in a real way. Our likelihood, our problems are called implicit, that there is in fact no likelihood of the data. Why? We are using the likelihood to fit the data all the time. Yes, but we are using approximated models. There is no, we have a simulation that produces templates of our data, but it's a forward model. It's not, we have no access to the actual generating distributions of our data. That is why we use these massive simulations. We cannot go back to the latent space and sample it with a mathematical function. We cannot differentiate it. This is called likelihood-free inference or simulation-based inference, okay? It's a big topic in statistics and as well as in physics. Now, in physics, what we get away with is we take approximations. So we find some smooth functions because we observed that the PDF of the proton, of the partons inside the proton are smooth. And so we sort of parameterize that, and we know that we don't expect much fluctuations. And we try to fit smooth distributions through our data points in the hope that we find a bump somewhere that will represent maybe a new resonance in the data. So I should say always in HEP, we do not know what is the true functional form of the data. So extracting inference from a spectrum is limited because you say, I see a deformation in the spectrum. Yes, but the deformation from what? You cannot say that there is a deformation if you don't know what the baseline is, right? So for instance, this is a classical example. We are looking for the Higgs boson. Now, back 13 years ago, we did not know that the Higgs boson existed. So we were looking for a bump in this kind of a distribution. And you see that it's smooth, but it's not even that smooth. For instance, here it seems to be curving downwards. So you need a way to parameterize this function such that you can then be sensitive to a Gaussian bump that sits on top of it. This is a tough problem. And a large group of people, starting 15 years ago, from Atlas and CMS, got together and they discussed statistical ways around it. And they defined a methodology to look for this kind of signal. This is a X to gamma gamma signal on top of very large backgrounds in a way that was statistically sound, that it was high power, that it was a high power of detecting a signal if there was a signal, and that it could be streamlined in calculations that could be done with suitable approximations. So you need to come up with a test statistic that can be approximated by, by functional forms and that has all of these good properties. It took 2 years to come up with a procedure. And there's a paper that describes these procedures in detail. But we don't want to get there, but I wanted to make the point that it is a complex problem, okay? So to find the right model, what you do is you throw a large number of possible models, or possible functional forms, and you try to fit the data with all of these functions and try to get some conclusions on which is the best function. Of course, if you use many parameters, the function becomes more flexible, right? Or if you use a neural network, it has 1 million parameters, it will fit the data perfectly. The neural networks are fitting functions, in fact, but very flexible. We don't want too much flexibility. If we have too much flexibility, it will wash away our signal because it will interpret it as just a vagary of the background somewhere. So you have to insert some rigidity in the model, and you do this by having few parameters. But few parameters will not fit the data very well, so you need to find a compromise, all right? And there's a solution. The solution that was used also in the X searches in many analyses in CMS and Atlas, we are using the F-test. And the F-test, the Fisher test, is basically based on the chi-squared. The chi-squared is a goodness of fit measure. We will discuss goodness of fit tomorrow. That tells you how probable it is that you see the data that you see if the model is the one that you specified. The chi-squared statistic is not the best way to compare data to a distribution because it does not know about the ordering of the deviations. If you have fluctuations somewhere, if you imagine that you have some data like this, and you have a model like this, you have a lot of fluctuation here, and it looks like it is something systematic, right? But the chi-squared maybe will be poor, but not too poor, let's say 5 per mil. And it will be the same chi-square if you have a situation where you have fluctuations, but they are casually spread here and there. It does not know about the order of these fluctuations. It makes a sum, okay? So the chi-squared is good for some things, but it's not good for this case. Here, maybe a Kolmogorov-Smirnov test statistic would do better. We will talk about that tomorrow, but the Fisher-F test compares the data to the model and tells you how good the model, the hypothesis is, if you want. Well, it tells you how well the data conforms to that. So the gist of it is that you try a certain function of, and you find that it produces a good fit. The chi-squared is not so bad. The probability of the chi-squared is large. But you are not satisfied about some features that the data possess that the model cannot capture. And you would like a better fit. So what do? You improve the model by adding parameters. So you add flexibility of the shape of the background to actually capture some of the feature in the data. So you try a more complex function by adding one or more parameters. Adding parameters always improves the chi-square. It means that it always increases the p-value of the fit. Because if the models are nested in one another, that means that there is one combination of parameters in the larger model that produces exactly the smaller model with fewer parameters. So for instance, a family of functions that has this nesting property is f equals a plus beta times x plus gamma times x squared. Okay, so this family of polynomials has this property that if you only take the smaller model, if you instead take the larger model, there will be a value of gamma for which you return to the smaller model. So these are nested models, okay? So adding parameters improves the chi-square. So did I do a good thing by adding one parameter? Yes, the chi-square improves, but see how much better the data to model is now. So should I take this more complex model or not? It is answered by the Fisher test. Well, you don't have to use your eye to decide how many parameters to use for your functional form. And there is an argument that's psychological that you will tend to choose always more complicated functions that it's required because you want your model to pass through all your data points. Instead, if it does, it is way too much overfitting. You should have a good model that passes only through 70% of the vertical bars of the data if the bars represent 1 sigma intervals, 68%. The other should be missed, but not by too much. All right, so Fisher's F test is a number, F. You extract a number, which is a function of your data, Y, and the function, which is the model. Okay, Y are the data, and F is the model you have chosen. So for instance, here I will have X, I will have some data points, and I will have a model. This is Y of X, but it's also F of X. Okay, this is F of X. And you are comparing the Y with F. And you are taking this difference squared, and you are taking the difference from one model, F1, and from a more complex model, maybe, F2, which has more parameters. And you take the difference of these two squared sums, you divide by the difference in the number of parameters of the two models. So if you are taking a quadratic and a cubic fit, the difference will be 1 parameter. You will have a sum of squares, which is larger for the more the 2-parameter, the 3-parameter model, and smaller for the 4-parameter model, because the 4-parameter model has managed to get closer to the data points. So this you divide by the sum for the more complex model divided by its own degrees of freedom. This number that you cook up has a Fisher distribution that is, it is sampled from a PDF, which is, sorry, it's a bit complicated. This number is sampled from this distribution if the added parameter of the cubic with respect to the quadratic, in our case, is not improving the model. What do you mean it's not improving the model? You said that you always improve the model if you make a more complex function. Yes, but we have to compare to a certain baseline probability. So what the Fisher test requires you to do is to set a type 1 error rate, an alpha level, a small p-value, 5%, 10%, depends if you are a physician, 5% is your type 1 error rate. If you are in particle physics, it's 3 × 10⁻⁷. But actually, to run the Fisher test, you will set the alpha value at 5% typically. Yes? Here. N is the number of data points. So n minus p2 is the number of degrees of freedom of the more complex model. So here I have an example for you. I have 10 data points with uncertainty bars. And I have 3 models, a constant, a linear, and a quadratic. Very simple, okay? So let's imagine that we have the data shown here, and we need to decide which model to pick. So let me run this, since you are so responsive with your answers. Which of these models would you prefer? Who likes the constant model? Raise your hands. 2. Who likes the linear model? Well, some 10 or 12, okay. Who likes the quadratic model? Okay, most people like the quadratic model. This conforms to my bias that we prefer complex models. The chi-square values have p-values that are all reasonable. You cannot really choose between a probability of 29% and 92%. Which one is better? Under the null hypothesis, probabilities are flat between 0 and 1. So you pick 29% or 90%, it doesn't really matter. You cannot really say that this is better than that. So we need to look a little bit further, okay? So the F-test will allow you to pick the best model, but you need to first specify a type 1 error rate. That is the amount of time, the fraction of times that you allow yourself to be fooled by the statistics of it. That means to say that if you say that alpha is 0.05, it means that you allow your Fisher test to choose a more complex model when the simpler model was the true one. And you can run pseudo experiments to verify this. But okay, let's pick alpha equals 5%. So I should have told you beforehand, let's fix the type 1 error rate at 5%, now raise your hands. But we played the game in a wrong way. Anyways, we define the probability that we observe an F value at least as extreme as the one in the data if it is drawn from a Fisher distribution with the corresponding degrees of freedom. So we are testing whether that value of F that we compute with the 2 distributions belongs to a Fisher distribution or not. Because remember, if it doesn't belong to a Fisher distribution, then we need to take the more complex model. Because what the Fisher distribution is telling you is, yes, you have a better chi-squared by this amount, and that's precisely what you should get if you are adding one parameter that doesn't belong. That means you can always make a more complex model, and it will reduce the chi-square, improve the chi-square by a certain amount, which is just a fluke, okay? So, okay, we are of course selecting large values of F, which are more extreme in this kind of game. So let's do the test. The macro that you have produces these graphs that compare one model to the other, and the distribution, the F distribution, here it is, the value of F, and the tail probability of the F test which is this value, which is this here, the cumulant, and you see we are very small p-value because the cumulant is almost already 1 by then. So from the constant to the linear, we see that there is evidence against the null hypothesis, which in this case was that the constant fit was all that was needed. So the p-value of this f value comparing constant to slope is 1.4%, which tells you that you have to choose the linear model over the constant because you have chosen a 5% alpha level, and here we are at 1.4%, so below that. So Fisher is saying, aha, this is a very small, this is a very large f value, so it's a very small p-value, so it's below the type 1 error rate that you set to yourself, so you should choose the more complex model. And now let's compare the linear to the quadratic, and we get this f value, and the p-value of this f number is 10.2%. So it's above 5%, and so this tells us that there is no evidence against the null hypothesis, which in this case is the linear slope. So you see, in this case, we should have chosen the linear slope, but that depends on the alpha level, right? Because if we want a 31% alpha levels, if we had said, if we had allowed ourselves to be wrong 30% of the time in choosing a more complex model, then we would be happy with the quadratic. Are there questions on this? It a little bit depends on what exactly it is that you want to do, because more complex models can be good in the sense that they can fit the data better, but you may be reading too much into the data that you have. The data that you have are providing a glimpse into your background distribution in your application. And if you fit it too much, then maybe 6 months later you have more data and you find out that your model was completely overfit. So it depends on many boundary conditions. I would advise to choose a type 1 error rate in the 5–10% range for this kind of applications. Seems like a legitimate thing to do. And the important thing is that you will have to put that number in your paper, because otherwise it's not replicable, okay? And then it's fine. We can play with the f-test with the macro that I provided. I don't think we have time for that. So this code that I provided can get you familiar with the f-test. You see this very nasty functional form, the Fisher distribution. It's implemented there. It's nice to play with it because you can change the number of events in the histogram. I mean, the number of beans, the number, you can choose the precision of this, and you can put yourself in various different situations. You sample this data from a certain distribution, and then you try to fit it with a different distribution. You can test various different functional forms. So these are polynomials, but you can do exponentials of polynomials, series or like this, where you have an exponential of this, or you can do other functional families, and you can learn something by playing with this. I think it's nice, and you will find that you gain a sensitivity on how well a fit can determine your choices. You can play with it and add the functionality, like adding new functions, adding new generation of data from different PDFs. But I don't have an example and an exercise for you for this evening on this one, unfortunately. Just play with it if you like. Now, let us go to confidence intervals. which refer to the topic that in statistics is called interval estimation, right? We have talked about point estimation all along, but estimating intervals is even trickier, okay? Now, please, if you have 1 minute to keep your eyes open and be awake this afternoon, let this be it, okay? Because it's important. What is the simplest confidence interval that you encounter in your practice? What?
I have a question.
Yes.
Let's say with some statistics, we come up with a model and we fit the model and we are getting chi-square degree of freedom to be 1. But let's say as the statistics increases with the data increasing, would it be correct to change the model if my chi-square value is changing and doing the F-test?
Yeah, so it's a very good question. So you have a model, you have decided on a model for your null hypothesis based on some data and based on running this test, and then you are confronted with the same experimental conditions and the same kind of sampling distributions, but the data get more and more precise, and therefore you may at some point fail the test. So the distributions that you had before now is not sufficient any longer. Or if you want, the more complex model that you discarded before now can be accepted at the same type 1 error rate, right? Should you change? What do you do? Should you change the model because the data has become more precise? Should you stick with the earlier model? I think you should change the model and be consistent with your type 1 error rate. Because the type 1 error rate tells you how much you are allowing yourself to be wrong, and that should be a constant of motion if you want. The more data you collect, the more insight you collect about how the background distributes, and so you are allowed to exploit this additional information. Sticking to the old model would be silly, I think. So yes, I would change the model.
When we are doing the experiment, we have signal along with the background. So to come up for the model of the background, mostly we study by the simulation how should the structure of a background look like, right? So as the statistics increases with the experiment, we'll be doing the similar simulations.
We will be doing, sorry?
The simulation still stays the same, right?
That is a big problem that we have. We run campaigns to have more and more simulation to keep up with the statistics of the data. And CMS and Atlas are trying to do this because indeed you start having a systematic uncertainty from the Monte Carlo statistic if you have too little statistic with respect to the data. Typically, you want the statistics of the simulations to be at least 4 times larger than the statistics of the data, so that the uncertainty that the statistical model provided by the Monte Carlo is producing is negligible with respect to the statistic uncertainty due to the data themselves. So you try to be in this situation. If you are not in that situation, then you have to bring in this systematic, and that is, yeah. We have another question there. The Fisher test can be run with just one distribution. It can be the simulation, it can be the data. If you want a model, you can derive the model from the simulation, then apply it to the data, but you can also derive the model from the data themselves. In fact, this is what has been done also for X searches. If you trust your Monte Carlo very much, you can do the tests on the simulation. And in that case, I would say that you should have, well, it's easy. You should have as much data as possible, but as much Monte Carlo as possible. But of course, if your statistic of the Monte Carlo simulation is much lower than the data, the F-test will not get you very far. It will probably give you a result that is insufficient to do a good job. It's yeah, it's a big problem because simulating large amounts of data are sometimes very cumbersome, right? No. Yes, I understand. If I understand the question is, I have a lot of Monte Carlo. I can do an F-test, and I get a very precise model because the F-test will like many parameters. But then I have few data point, much less data to fit, and so is this producing a problem? It is not producing a problem if the Monte Carlo can be trusted. If you have a high fidelity simulation, you can trust that the Monte Carlo is producing a distribution that is equal to the one in the data, then you are allowed to use all the power of the information that you have to produce a very complex model for the distribution and then apply it to very scarce data. This is done actually routinely, but you have to be doing lots of validation of your Monte Carlo in sidebands, in orthogonal samples where you have more statistics. If you can do that, you will validate your Monte Carlo, and then you will be able to exploit this information. I don't see a problem in changing the amount of data. Because you are within a constrained system where you have a certain amount of data, you fit it with different models, but the data doesn't change. Okay. So, your moment of concentration for today. The simplest confidence interval is the one standard deviation. The one that gives you one sigma interval, it should cover 68.3% of the possibilities, right? Because that's one sigma, the integral of a Gaussian from -1 sigma to +1 sigma is 68.3%. So this is a relevant number which we refer to when we do 1 sigma error bars, even if we are not sampling from the Gaussian. So we use it as a way of talking, of communicating results. It's a standard of communication, okay? So for example, we have an observation of a random variable from an hypothesized PDF with it unknown. The set of data allows to construct an estimator. We can use an analytic method or the RCF bound or Monte Carlo sampling, and we can estimate the standard deviation. So with the variance with Rao-Cramer-Frechet from a likelihood or something of the estimator. So we report in an article this value. We report the estimator value, and we report its standard deviation. What do we mean when we report these two numbers? Be careful, I'm reporting theta hat plus or minus sigma hat of theta hat. You know, hat means estimate of. So we are reporting an estimate of the parameter plus or minus an estimate of the variance of the estimator. What it really means is not compressible in less than 3 lines of text in font 22. Okay, so it is something that requires some text. It means that in repeated estimates, based on the same number of observation of X, conditioning, we will get to it tomorrow afternoon, or 2 days. Based on the same number of observation, repeated estimates, my estimator would distribute according to a PDF, G of theta hat, we wrote it before, centered around the true value theta, with a true standard deviation sigma of theta hat. And the true value and the true RMS of the estimator are respectively estimated by sigma hat, by theta hat and sigma hat of theta hat. So this is not as trivial as, well, it doesn't sound trivial, and it isn't. Okay, so you need to think about it. We are estimating something, and we are associating an uncertainty to it. The uncertainty is the uncertainty we estimate on the estimator. It's not a true uncertainty of the estimator. It's an estimate of the uncertainty of the estimator, okay? So this is what we do when we report 3 plus or minus 1.5, okay? So when you see a number with an uncertainty, think at all the cuisine that there is behind it. If it is done correctly, it is a lot of it. And because most of the times it's not Gaussian, the world is not Gaussian in small sample limit, unfortunately, this is a complicated construction. And statistics deals with point estimation and interval estimation, and they are two estimation problems. Okay? Are there questions? Very good. So when we go in the large sample limit, the distribution of the estimator is a Gaussian function. That's very good, because if it's a Gaussian function, most of our problems go away. But in most interesting cases for physics, G is not a Gaussian. The large sample limit doesn't hold. 1 sigma intervals do not cover as they should at 68.3%. And we have to be careful how we construct our intervals. But it all revolves around the PDF. We need to know the PDF if we are to do a good job. Then there is the guy, Jerzy Neyman, that really helped in constructing intervals that work. Intervals that work are intervals that don't betray you. They actually capture at least 68.3% or at least 95%, whatever is your type 1 error rate that you stated at the beginning of the day. They cover the true value of the parameter. So what the Neyman confidence interval recipe is a procedure by means of which you can extract intervals around your estimates. So the first thing you do as you wake up in the morning is you specify a model which provides the probability density function of some observable being found for each value of the unknown parameter of interest. So you specify the model, P of x given mu. Mu is your value of interest, x is the data that you collect. And then also you choose, as you hit the mat on the floor with your left foot, as you wake up, you choose a type 1 error rate. It could be 31.8%, it could be 5%. And then the fun begins. You use your PDF. For each value of the true quantity you want to estimate, you evaluate the PDF. The PDF will have a certain shape. It will not be Gaussian typically. It will be something, whatever it is. And this is for a value of mu equals 5. And then you draw a horizontal acceptance interval such that the probability that you find x in this interval is 1 minus alpha, given mu equals 5. So if this is the axis of x, you are asked to produce an interval that contains 1 minus alpha of the probability. How can I do that? There are an infinite number of ways to do this if I have a continuous distribution. Because all I'm asked to do is to produce an integral that leaves 5% outside of it. So I need to get x1 and x2, and there's an infinite number of ways. I could even imagine that I take an interval that is not even simply connected, and I say I take this part and I take this part, and then I like this little bit here. You are perfectly allowed to do this by this stipulation. Well, we talk about an interval, but an interval in the extended sense can be a collection of smaller intervals, okay? And if you have to do with discrete distribution, you actually have to do that. Here is the Neyman confidence interval belt for a case where you measure a parameter x and there is a true value that you don't know on the vertical axis. So what I want to mention is that there are infinitely many ways to extract these intervals, but here I have already extracted intervals, assuming that there's a continuous PDF lying somewhere that moves to the right as the x becomes larger, okay? So if x is equal to 5, the likely values of mu are in this area. If x is equal to 2, the likely values of mu are in this area. But for every mu, if I take mu equals 5, for instance, there is a well-defined interval x1 to x2 that covers the region between 3.5 and 4.8 or something, for instance. So for each mu, you can draw this horizontal interval. But the problem is that there are infinitely many ways to derive these intervals, and so we need a prescription, an ordering rule. And the ordering rule for extracting upper limits, we'll see how that works. We need to integrate the PDF from x to infinity. So if you have a PDF and you want upper limits, you need to put all the 5% that is your type 1 error rate probability on the left. If instead you want lower limits, you have to do the opposite. You will take a upper tail and you will find the point where you have 5%. And in this case, you will have x1 here and you will have x2 at infinity. In the other case, you will have x1 at minus infinity and you will have x2 at this point. But if you want an interval, you can choose a central interval. A central interval is the interval that leaves half of 1 minus alpha here, sorry, alpha of alpha here, and half of alpha probability here. This is a central interval, okay? But you could have shortest intervals that they could not be the central intervals. If, for instance, you have a complicated distribution function, the shortest interval that contains 95% of this PDF might not be central. It might be something that is skewed towards the left or something like that. Okay, so you have to have a prescription. You have to have a type 1 error rate. You have to know the PDF. And then you can come up with a confidence belt. And the confidence belt will allow you to play a trick. You measure x. Now you measure x. You have not measured x until you have done the confidence belt. The confidence belt was possible to draw by just knowing the PDF of the data before you collected the actual measurement, okay? Now you collect the measurement and you find this point, 3.25, I don't know. And you draw a vertical line this time. Once you have the vertical line, you get the intercepts with the confidence belt. The intercept with the confidence belt will define two numbers, mu1 and mu2. That is the confidence, the 95% or whatever it is, confidence level interval on the true value of the parameter. So you see that it is a rather complicated recipe, but it is a recipe that is guaranteed to cover. And we'll see what coverage is in a second. So this confidence interval is the union of all the values of mu that are intercepted by this line, okay? And be careful, because we might be in a situation when we have more disconnected regions, for instance, because we might be in that situation. The confidence belt might not even be connected. It might be something like this, for instance, where you have a hole here. So if I measure x here, I could have the possible values of mu would be these, okay? So I would have the interval from 0 to 2 and from 4 to 6. This is totally legal. And it is an interval that covers at the required type 1 error rate. Now, I was talking about coverage. What is coverage? No. What is a vector? You studied mathematics, so you should be able to answer this question. Who wants to give it a stab? What is a vector? Somebody who tries. Just try it. We will forget who you are tomorrow. Nobody wants to try. So it's something with a magnitude and a director. That's an operative definition that's very good. And we know what a vector is if you tell it this way. But I think there is a better definition. A tensor over rank 1 is a more technical definition. It also more or less stays on the same line of defining an object through its attributes. But actually, if you think about it, a vector is not defined by its own attributes. A vector is defined better, if you think about it, if you specify the properties of what? Not of himself, but of the space that contains it. So a vector is an element of a vector space. Thank you very much. I don't know anything yet. Yes, but that's the best mathematical definition, right? I have not said anything about how the vector behaves, but actually I'm saying everything if you know what a vector space is, because it is a vector space that has the properties. It's not a vector. If you sit on a vector, you don't know that there are some symmetry properties. It's like sitting on a dominion or a ferromagnet. You don't know that you are in a symmetric system. If you take one vacuum of the Higgs, you don't know that there is a symmetry of the standard model, right? But the symmetry exists, it's just hidden. So a vector is an element of a vector space, and it is the set that contains those properties. Similarly, a confidence interval like the one we drew is not particular per se. It doesn't have properties per se. It is an element of a confidence set. And it is the confidence set that possesses property of coverage. It is not the individual element that you so tidily wrote that has the property of coverage. Think about it this way again. We drew an interval here. Are we guaranteed that mu is within this interval? No, we are guaranteed at 95%. But this is a statistical statement. But in fact, this interval either contains the true value or it doesn't. We say 95%, why? Because we are not talking about that interval. We are talking about the possible intervals of a set. It is the set that has the property of 95% coverage. It is not this poor guy. This poor guy has either 0 or 100% coverage. But the set has 95% coverage property, okay? So coverage, be careful, is a property of a set. And it depends on how your procedure extracted the belt, okay? And it's only upon sampling that you get the properties right. Any single interval either covers at 100% or doesn't cover the true value, and you don't know it. So if you let the unknown true value of mu be mu true, upon repeated experiments, the confidence intervals obtained will have different endpoints, depending on the random variable x. A fraction 1 over alpha, 1 minus alpha of the Neyman intervals will contain, in the sense that they cover, the true fixed but unknown mu t. So in this sense, the probability that the true value is within this interval is the confidence level, and it's 1 minus alpha. And I am allowed, in a sense of speaking, of a probability of a true value because of my construction making mu1 and mu2 the random variables in this game. So the random variables are mu1 and mu2, and that is what actually allows me to make this statement. Because I'm a frequentist, I cannot speak of the probability of a parameter of nature. But here I'm implicitly talking about the probability of the two parameters mu1 and mu2. That is what makes this statement correct. The random variables are mu1 and mu2, and they depend on x, of course. Coverage is a property of the set. And for a frequentist, the interval either covers or does not cover, regardless of alpha. And the classic false statement you should now be able to avoid making, you will remember that yesterday morning I was saying all these things that shouldn't be said. The probability that the true value is within mu1 and mu2 is 68%. This is not true. This is a statement that doesn't hold because it's only the set that has this property, not the individual interval you came up with. Sorry, and this doesn't read, but the confidence interval instead does consist of those values of mu for which the observed x is among the most probable. But okay. And also repeated sampling does not mean that I need to have always the same conditions. I could assemble results from different experiments of the same physical quantity, the top mass measured in CDF, CMS, D0, Atlas. They all quote 1 sigma intervals at 68.3%. I can combine these results, and all in all, they make a confidence set because they are drawn with the same ordering principle, if you want, central intervals, and at the same type 1 error rate. And then I can construct, I have a confidence set. It doesn't need to be the same experiment that measures this thing multiple times. Okay, so now we are ready to do some more fiddling with computer code by looking at the coverage of likelihood intervals, because you will remember that we did the loaded die example, and maybe some of you did fiddle with that piece of code and produced the toy experiments of die throwing and extracting the likelihood of a certain load on the die. Now, I have this macro on that same area, you know, that not only throws the die and extract the value of the load plus or minus its uncertainty by computing the uncertainty with the Rao-Cramer-Frechet bound, but it does this multiple times for any assumptions on the load. So I'm looping on the load from minus 1/3 to plus 2/3, or minus 1/6 to plus 1/3. And for every value of the load, I'm making multiple times this estimation so that I get an estimate of the coverage probability of my likelihood intervals, because I have every time an estimate with an error bar, and I can check whether I am getting the true value within my bounds or not. And so I can see whether the likelihood intervals cover or don't cover. Let's see. If it works. I need my glasses though. So you can see the screen. So this macro allows me to specify a number of throws of the die. Let's put it a small number, 20. A number of repetitions, let's say 1,000, and a type 1 error rate, which could be 5%. You can keep the default. So this is the result of the test. you see from minus 1/6 and plus 1/3, where did I put the, oh yeah, the pointer. What I have done is I have extracted the probability that the intervals, the likelihood intervals, cover the true value as a function of the true value. This is the scatter plot of the values of t that I extract for every value of t that is true. And you will see that this is a ragged distribution. Why? Because I have only a few die throws. And so the values of t that I can estimate are not continuous. They depend on this discrete statistic of the number of ones and sixes that I have extracted from the counting. But still, I can integrate and get how often this result is within the uncertainty bound given by the Rao-Cramer-Frechet approximation for every value of the load. And you see that this is a 31.8 coverage probability that I have requested, 1 sigma intervals. And I am almost at 68% here. But then the coverage properties go really awry. You see, for small values of the load and for large values of the load, these intervals really cover much, much less than the stated 1 sigma intervals. So this is what I was saying before. Likelihood intervals should not be trusted in the regions close to the bounds of a parameter, because the uncertainty is not very well estimated by Rao-Cramer-Frechet bound, but also the values themselves can be significantly biased. And the two things go together. And there's a further thing that I have plotted here, which actually belongs to tomorrow's lecture, but I can already make an anticipation. Do you know what power is? Well, power, it's good to have power. It's good in statistics to have power. Power is the capability of discerning an hypothesis from a null hypothesis. So let's say that I'm doing a hypothesis test, we'll see it tomorrow. I have the null hypothesis, the standard model is true, and I have the alternate hypothesis. The standard model is true, but there is also a resonance at 750 GeV. So this is the alternative hypothesis, and my power is how often I am able to choose the alternative hypothesis when I do hypothesis testing based on the data that I collect. So, and the procedure that I use to analyze the data and to choose which hypothesis is correct. Basically, having a power of 1 means that if the alternative hypothesis is correct, I will always choose the alternative hypothesis. But this is impossible. This is impossible because you will, in order to have 100% power, you will have always 100% fake rate also, so that you will be always choosing the alternative hypothesis. That is how you have 1 power. But you will have also a type 1 error rate, which is 1. Instead, you want to have a low error type 1 error rate. What is the type 1 error rate? The probability that you incorrectly choose the alternative hypothesis. You want this number to be small. If you go to test for COVID or AIDS or whatever, you want a medical test that doesn't tell you that you have that sickness if you don't have it, right? You want them to spot if you have the sickness, you want them to have high power, but you don't want a large type 1 error rate. So the two are conflicting criteria. Now, what you see here is the power of spotting the alternative hypothesis from the null. What is the null hypothesis in the die throw example? 0. The null hypothesis is the hypothesis that there is 0 load on the die. This is how we constructed it. And And this is how the power curve behaves as a function of the load on the die. You can construct it by looking at how many times your interval does not contain 0 when the true value of the load is not 0. Okay? I mean, we will go to hypothesis testing in more detail tomorrow. Let's run it again with more die throws so that it becomes a little bit smoother. And let's also specify a small type 1 error rate to see what happens, because I don't know actually what was the default here. You see, it's very fast to run this kind of test. And you see that if you have many die throws, now there is a much better correspondence between the estimated load and the true load. This starts to be a very good correlation curve. And you see that in this case, the coverage at 1 sigma remains very good throughout, but it still drops or even goes to 1. So you see, these coverage properties are unpredictable, and but it is the central value that is screwed up on the extreme. And you see, we see it better because in the other case we couldn't see it well. But we see it better that with a 5% type 1 error rate, that is exactly the power when the null hypothesis is true. When the null hypothesis is true, that is when the load is 0, you should find that the power is exactly the type 1 error rate. And you see that we have much higher power throughout, except from the region where we cannot really distinguish the true from the null hypothesis from the alternative hypothesis that the load is different from 0, is of course the region where the true load is close to 0. But since we have many die throws in each pseudo experiment, the probability that we accept the alternate hypothesis, that is, that we find a load that is not compatible with 0, is of course much larger. Questions on this? Now you have the macro, and now you can consider doing this kind of tests in your problem, because you can code it up, you can code pseudo experiments, you can sample your PDFs, you can extract coverage intervals, and you can test how well they cover, your intervals cover. Okay, so you should do it because you can do it, right? Okay, so let me move towards the conclusion of today's lecture. Good. So I think I made the point that the likelihood intervals have some shortcomings. Likelihood method, great. Constraint parameters, be careful at the extremes, okay? All right, so more on coverage. Yeah, we are almost done. So coverage is guaranteed by name and construction, but sometimes we have a PDF which is discrete. How do we find a interval that covers at 68.3% if we have a chunky PDF? I start integrating 20%, 45%, 79%. No, wait a minute, I don't want to get to 79. I want only 68, but how do I get there? Maybe I can integrate this way. No, it goes to 85. So if you have discrete distribution of probability, you cannot get exact coverage. And then a frequentist will ask you to overcover. You will have to exceed the nominal coverage to be covering correctly. So you will have to accept overcoverage. This is a classical example. Say that you have a binomial process where you have a certain number of trials, and this is the fraction of successes over trials. And I don't even remember how many trials there are in this example, but this in blue is the coverage of the Klopper-Pearson's intervals, that are intervals that are constructed for the binomial in a special way. well, they are obtained exactly from the Neyman construction, and they overcover. They are always above 68%. The Wald interval, instead, that is the one of getting the estimate of the binomial the binomial ratio with your number of successes over trials, this is a bad undercovering procedure. So this problem, the coverage of the binomial intervals, is one that has spurred many papers. Okay, and there are at least 5 or 6 well-known recipes: Agresti-Cool, Lancaster mid-P, Wilson score interval, Klopper-Pearson interval, Wald intervals. I don't even remember all of them. But, and they all have different properties. The Wald interval is the worst of them. Don't use the Wald interval. If you can, please use the Wilson score interval, which is very similar, very simple to extract. Undercoverage, on the other hand, is very bad. So we accept overcoverage because we want to provide our consumers with an interval that at least has the property of coverage that we stated. And instead, we happen that sometimes we do procedures in our daily practice that will guarantee that you undercover. So for instance, if you decide whether to quote an upper limit or a confidence interval a posteriori, if we change that is the kind of result that you want to produce after looking at the data, this will undercover. Your intervals will be screwed up. If you modify the details of the analysis, like after opening the box in a blind analysis because something didn't look right after looking at the data in your background estimate, for instance, this will undercover. Also, not publishing results that are controversial will cause your uncertainty bars to be wrong. And this is peculiar, and this is, I made a study, this is the ratio of the true uncertainty versus the measured uncertainty versus the true uncertainty, so that if you are below 1, you are undercovering. And this is as a function of the true effect, physical effect. And this is extracted by assuming that the collaboration withholds results that are controversial by being away from the mean by 3 standard deviation or something like that. Because it happens in CMS and it happens in Atlas. I know that if a result, you open the box, you are looking for a new particle, you find a 2.8 sigma result, an effect which is almost evidence for the particle that you are looking for. And there will be the physics coordinator that says, wait a minute, I don't want this result to go out. I think there is something fishy in your background estimate. Let's sit on it, and maybe we will publish with the next iteration of the data. That is wrong. That is going to modify the coverage properties of all the physics results that collaboration produces. Because those that pass to the public are only those that are passed through this filter that selected out some results in an arbitrary way based on the observed characteristics. So beware, okay? And I think I need to stop here because I ran out of time. But we have just 2 or 3 slides to take care of tomorrow before we go into hypothesis testing and other things. So thank you, and if you have questions. No questions? Everything was very clear. Very good. The correct answer is 1.8. But to know it, you need to know how to invert the conditionality with the Neyman procedure. And the first person who did this was Garwood in 1950. He took the Poisson, inverted the test with Neyman confidence interval, and you can read off the upper limit when you observe 0 at 1 sigma at 31.8 type 1 error rate, and you get 1.8. And if you do rule-fit histograms, the default will be to draw an error bar that extends up to 1.2. And that is because it mistakenly takes the two-sided interval also for n equals 0, when you should take only the one-sided interval for n equals 0. When n equals 1, then you have an error bar that covers on both sides. Yeah, but beware. That is a very good question and for you, but you can look it up now on the root, what they do. And in CMS, we often have the situation that we publish results with the wrong error bars at 0. That is the error bars that extend to 1.2. That is because that is the defaulting root, unfortunately. Oh, okay.